Okay, so here are the questions we have now. You wanted the 2.1 questions. Can you go ahead and read number 12 to me?
Number 12 is the frequency, and then it's in parentheses hertz of a photon if 10 to the power of 20 of these photons combined have an energy of 1.00 joules.
How many photons?
10 to the 20th power.
And they have the total energy of?
Just 1.00 joules.
Okay, so what is the frequency in hertz if 10 to the 20 photons have a total energy of 1 joule? Okay, so I'm going to do my typical thing. We're going to look at the explicit information, and we're going to look at the result we want to get, and then we have to figure out the implied information. Okay, so the explicit information is I've got a number of photons is 10 to the 20, and I've got an energy that's a total energy of all of those photons together is 1.00 joules. And I know that I want a result that's frequency. So if we have no idea where to start in this problem, this is how I start problems, right? I'm like, okay, I have no idea how to start. I'm just going to write down the things that I know. Like I write down the numbers, and I write down what I'm trying to get to. And then I look at these things, and I say, okay, is there some way that number, energy, and frequency relate to each other? I don't really have a good idea that relates those three things. Like if I'm looking at the equation sheet, I don't have something that relates those three things directly to each other. But I know there's something that relates energy and frequency together. But it's not the energy total. It's the energy of a single photon is h nu. I'm like, okay. Well, if that's the energy of one photon, and this is one of the things that's not usually explicitly written. This is the energy for one photon. What would be the energy if I had 2 photons? Right, if I had an energy total, what would be my energy if I had 2 photons? 2 times that. What would be my energy if I had 10 photons?
3 times.
Right, what if I had 50 photons?
Just 50 times.
50 times, right? So it's just going to be my energy total is going to be the number of photons times the energy of a photon. Right, and that's a pretty funny equation to write down. It says like, oh, if you have 30 things, 30 times is the energy, right? It seems kind of obvious when I say it. But we never wrote that down as an equation in class. The textbook talks about it, and it's just this idea of multiple things add their energies together. Now, with that thinking, so this one is kind of the important thing to think about, because this is the one that really gets people, is this idea of like, well, how do you have the energy of multiple photons? And it's really the fact that when we write down this equation, it's the energy of a single photon. So when we calculate the energy here, we just write it down as joules, but it's really joules per photon. And then if we put lots of photons together, it's just that photon energy times the number of photons we have. And now we have a way that we can use this number and leave that number unsolved. So now I just rearrange these things. I drop my energy of photon in here, and I end up getting my energy total is equal to the number of photons times h nu, energy of the photon.
Sorry, do you insert your values first, or do you rearrange your
I usually rearrange first, right? Because if I start plugging values in, sometimes I lose track of like which way I'm going. So I know that I want to get a result of frequency. You can do it either way. You can do it the way that you're more comfortable with.
Easier.
Yeah, do it the way that's easier for you.
No, like I'm asking like what.
Oh, for me, it's always like I do a better job working with the variables. I'm less like when I punch things into my calculator, that's where I'm most likely to make a mistake. So I try to do that all at the end at once.
Oh, okay.
Because calculator mistakes are the bane of my existence. So now I can go ahead and I can just rearrange this. So I have my energy total divided by the number of photons times Planck's constant equals frequency. So now I can do this all with one thing in my calculator, which is why I like to do the rearrange first. right? Plus, like, if I was trying to do this, I could do my energy of total. Like, I don't even know how plugging numbers in would go very well. Total, number of photon, H, it would be the same. It'd come out the same. For me, I find that the rearranging first makes it so I'm less likely to make a mistake. For you, you might find it a different way. So try it. Try doing it where you plug the numbers in first. Try doing where you rearrange first. See which one works better for you. Before we plug it into the calculator and start trying to get numbers for this, I like to do one more thing. And I like to think, okay, what is a reasonable answer going to be? So what's a reasonable frequency for photons? I don't really know, right? Especially since, like, I don't know what wave, like, usually I use the, like, if it's visible, I kind of know, I have an idea, but, like, I've got 10 to the 20, I've got some total energy. So the only ballpark idea I have is that I know visible spectrum is, like, 1 times 10 to the 14 hertz. So I'm expecting pretty big numbers, like 10 to the 14, 10 to the 13, 10 to the 12, 10 to the 15, something in that range. So that's what I'm expecting, and I only know that because of some of the problems we did earlier in the quarter where we had some terahertz frequencies, right? And so we had numbers that were like 10 to the 14. I happen to remember it. It's okay if you have like no sense of like, well, I don't know what the frequency is. If it was wavelength, I'd know the wavelength should be like nanometers. But the frequencies, I'm less good with the frequencies. So let's calculate a value and see what we get. I have a calculator here. Calculator. Okay, so I'm going to plug in my values. It's going to be pretty easy to plug these in. I'm going to have 1 times, I'm going to have 1, I'm going to have a 10 to the 20, I'm going to have a 6.626 times 10 to the minus 34. If you're plugging it into your calculator, do not forget your parenthesis. That negative 34 will end up on top if you don't do that. Oh, this is going to work out great. Oh, except for I forgot. I had a typo. 20. Now, why am I saying it's going to work out great? I think we're going to get a frequency on the order of 10 to the 14. I'm going to do 1 times 10 to the power of 20 times 6.626 times 10 to the negative 34 inverse. What'd you get?
I got 1.51 times 10 to the power of 13.
Perfect, so did I. 1.51. 1.51 times, oh, I didn't give myself enough space there. Here, let's just do this real quick. 6.626 times 10 to the negative 34. Just make that smaller so I can do my 1.51 times 10 to the 13 hertz. This would be like 15.1 terahertz. It's kind of on the scale we were expecting. If I wanted to double check this, I could convert, because like, again, I said I'm not very good with hertz. I could convert this to wavelength and see what wavelength it is. There's nothing in the problem that asks us to do that. Question?
Oh, go ahead.
I'm gonna go for it.
I was going to say, so ET is just total energy.
Yeah.
But in this case, it's just 1, because that's what the problem
Yeah,
is.
because they gave us a total energy of 1.
So if it was like, let's just say 5.0 joules, we would put 5 instead
Yeah.
of 1. Okay.
Yeah.
Technically the same. I was like, so, because when I did it, I just assumed like, well, how it was 1, so I was like, okay, like, I just literally just times the number of photons, or the NP times H, and that's it.
Yeah, totally
Okay.
works, right? And the reason that works out is because this problem specifically has the total energy equal to 1. You could have total energy equal to any number. You could have it be 20 joules. You could have it be 0.035 joules. And it could be any number. For this problem, it was just 1 joule, so we just end up with 1 over. How would I convert this to wavelength? What's new? C over lambda. So I would do lambda equals C over nu. I'd inverse this times 2.99 times 10 to the 8th. Oh, that's actually in the microwave range. So not even in nanometers, but still reasonable. It's like a microwave energy. Didn't have a lot of good conversion problems in there. but we'll do some conversions in a minute. Any other questions on this one, or should we try number 13? Okay. So I'm going to erase this. Okay. Number 13.
All right. What is the speed of light with a frequency of 2.4 times 10 to the 13, and it's 1 over s?
Speed of light?
Yeah, speed of light with a frequency of 2.4 times 10 to the 13.
Oh, I see why I'm confused.
Oh, okay.
It's a trick question. What's the frequency?
2.4 times 10 to the 13.
Hertz?
Yeah.
Or inverse seconds.
Yeah, inverse seconds. Yeah.
Which is the same as hertz.
And then it's just give your answer in meters per second.
What's the speed of light?
Oh, what?
Oh, I just say 3.0 times 10 to the 8th, but 2.9.
Yeah, I just say 2.
Yeah.
It says what's the speed of light in meters per second.
It turns
my
out
God.
that like
That like threw me off.
yeah, so it doesn't matter what the frequency is. The speed of light is the same. So it's like a kind of that's why I was like, wait, that doesn't like that's why I was like, this is what it tells you, and then I was like, oh, it's a trick question, right? So the whole idea here is the fact that, and this is kind of important for light, right? And that's part of why this question is here, because it turns out if you're looking at sound waves or if you're looking at these other waves, the speed of the wave in air or in the speed of the wave in air or in water, wherever you're looking, actually does depend to some degree on the frequency, right? You have, like what we have, when we have nu lambda equals c, c is a constant for us. Most waves have nu lambda equals v. So your velocity depends on your wavelength and your frequency. And you can have different velocities of your waves for sound waves and water waves. For light, that's a constant. And so it doesn't matter what the frequency is. It's still 2.99 times 10 to the 8. Yeah, and so that's kind of, again, one of those really weird things that happens with light that kind of makes light different than other waves. Okay, so that got rid of the 2.1s. Let's look at 2.2, number 1, and we're going to use that to do some unit analysis as well. Do you have it ready?
Sorry, it's still there.
Okay, you load that. I'll get this ready because we're switching over.
Oh, it's 2.2.
Mm-hmm. number 1. Now it's a Rydberg equation one.
It says it's just for like the quantum numbers. It says explain what it means for energy to be quantized.
Oh.
Yeah, it says why is this term important for understanding energy levels in the atom? Are electron energies always quantized?
Quantized. Yeah.
Quantized.
Yeah.
Because I understand like.
This is a conversation problem.
Oh.
Yeah, this is like a. Is there anything for you to hit submit?
No.
No. So this is a total
These are just, like,
conversation problem.
conceptuals.
Yeah, these are really good for getting ready for the exam because like the writing assignment we did on Thursday, it's like it's not worth anything, but it's just like, can you explain this idea to somebody? Can you talk this through? And man, it's always like, I wish I could make the exams like 5 hours long because there's so many questions I could ask. Like, and then office hours, I always think of like other better questions. It's gonna be like an hour and a half. But like I was like even in office hours today, like not the problems we've done, but I was like, oh, there's like 3 other problems I could do. But like I can't fit them all on, so I have to pick. And then I always feel bad because I'm like, what if you study something that I don't put on there, but then you don't study anything? It's just like, well, if it was 5 hours long, I'd fit everything on it and be fine. In any case, so we have to figure out this idea of what it means for energy to be quantized. Now this is a really weird idea. So this gets to the whole like walking around with the glasses on thing we did last week, if you were there on Tuesday, right? So we walked around, and I'm going to look at two different spectrum, right? So we're going to look at hydrogen, and we're going to look at mercury, and we're going to look at the sun. We're not going to look at the sun, but we're going to like pretend what would happen if we did look at the sun. Let me see here. What do I got? I don't have. Oh, I did it online. That's why. Okay. So when we look at hydrogen, we see only a few. Well, let's do the sun first, right? For the sun, we see like red. We see orange. I don't have a yellow marker, but you see yellow show up here. I'll just put this yellow happy face there for the yellow. You see yellow show up. Then you see green show up. Then you see blue show up. And you see this like full rainbow. Blue shows up. I got some. Did I accidentally put black ink in my blue? Hope not. And then you see, I dropped my, where'd my purple go? Ah, here it is. Right, you see a full rainbow. You see every color, and it's just like constant. And so people thought that like that's how light behaves. You should see full rainbow of everything. So when you go and look at hydrogen, because the sun is mostly hydrogen, when we go and look at hydrogen, we should see a full rainbow. Is that what we saw when we looked at the hydrogen lamp?
What color was it?
It was one of the purple lamps.
Oh, no.
So we saw a red line, a blue line, and a purple line. We're like, well, that's weird. Why didn't we see a full rainbow? Why don't we see every possible energy? We see discrete energies. And then we went and looked at mercury, and if I remember correctly, mercury has, again, I'll use this because I don't have a yellow marker. It has a yellow, it has a green, and it has a blue. And that's what mercury has. And every lamp we looked at, right, we put on those glasses and we looked at lamp after lamp after lamp, and they all had these like discrete lines, where each line, each wavelength corresponds to a specific energy, particular quantity of energy. And that's really weird. Right? Nothing else that, like everything we deal with in our day-to-day lives on like the human scale, there's none of this like specific amount things, right? It's like you can take your oven dial and you can turn it to any temperature. It's not like you have to have it on low, medium, or high. It's like any temperature. So this was really strange to people. And that's where the Bohr model and then the quantum model, the Rydberg model kind of come together. And we say, well, this is only possible if, for our energy scale, there's like a first answer, and then there's a second answer, and then there's a third answer, and then there's a fourth answer going up and up and up. But there's discrete energy levels. So that's another word we use, discrete, like where there's only specific values, right? And so that is, when you have this energy that's only particular quantities are allowed, we call it a quanta of energy. And when you're doing anything with quantas of energy, that's a fancy way of saying that's where you're doing quantum mechanics. And the phrase you use to say like the energy is in specific quantities is you say it's quantized, right? So you notice the word quantity and quantized, they're like, it's the same root.
Okay.
So this whole idea of why does this matter? What's it do? Well, it was a weird thing for people to propose, and it was a weird thing for it to be that it worked out that was true. And it's totally changed our understanding of physics and chemistry and the way that the atomic scale world behaves.
So are they always quantized?
Yeah.
Okay.
They're always quantized.
So I mean, it says, why is this term important for understanding energy levels in the atom?
Yeah. So that's this, right? It's the fact that so like that is a weird way to phrase it, because it's like, well, you wouldn't have energy levels in an atom if it wasn't quantized. You'd have energy bands of like billions and billions of possibilities all stacked on top of each other. Mm-hmm. But it's quantized, so you have specific energy levels that are allowed and gaps where it's not allowed, right? We never have a 1.5. You never have an n equals 1.5. It's 1 or 2 or 3, nothing in between. And that's where that specific quantity and that quantized idea come from.
Is there a reason why it's only whole numbers?
Yes.
Okay.
So, like, I kind of have given you the short answer in the idea that, like, there are particularly allowed answers. The longer answer, and the reason I paused dramatically and was like, that's all I'm going to say, is because the deeper answers in the mathematics that we're skipping. When you start looking at how an electron behaves in a confined space, the common example is a particle in a box, which is not like it's pretty close to an atom, right? But like you have a particle, an electron stuck inside of a confined space. It turns out that there are answers that give you an energy value and like a wave function that exists, and an answer that would be a non-allowed energy value, that you'd get a wave function that would essentially unravel itself and destroy itself. Through the idea is constructive interference versus destructive interference, kind of like a nice sound of music versus like a dissonant sound of music. And the reason I use sound and music as an analogy is because it's wave equations, and sound is also waves, and so it's a pretty good, like, it's not a perfect analogy because, you know, electrons are not making sounds per se, but it is a wave equation, and we understand sounds when, like, you play 2 keys on the piano and it like is a nice sound, and you play 2 keys and it like sounds terrible. I don't know if you know that. Like,
No, I
okay,
understand that.
cool.
So,
So-
overall, it just means that it's like
Specific values, right?
Specific, okay.
Specific quantities are allowed,
Thank you.
and all other quantities are not allowed.
Thank you.
Yeah. What about number 11?
It says calculate the shortest wavelength, and then in parentheses nanometers emitted by an electron in a hydrogen atom undergoing a transition from the N equals 4 level.
I should have. So, like, I wanted you to read that so I could see what kind of, if there was some good unit conversion in there. I'm going to have to ask you to read it again because I didn't write it down.
Okay.
But give me just a moment. Let me erase the board. Are we good on this one? Okay. Okay, so, yeah, quantization. Now, one of the consequences of quantization, or one of the ways that quantization was confirmed, rather, is Rydberg equation. So, we wanted to find the wavelength.
Yeah, the shortest wavelength emitted by an electron in a hydrogen atom undergoing a transition from the N equals 4 level.
Okay, so we got a couple important things here for our thinking in terms of explicit and our result. Our result is we want to find wavelength. Our explicit is, there's a couple things. We know the N initial is equal to 4. The N final is something. We know it's hydrogen, so Z equals 1. The implied information. And actually, I'm going to write some more explicit things down as we start to look at the implied information. Because there's actually there's 2 other really important key terms that imply information here. So before we do that, let's go ahead and see, I've got wavelength, I've got 2 n. Whenever I've got 2 n values, I'm probably using this thing, delta E equals negative Z squared RH, 1 over n final squared minus 1 over n initial squared, right, that thing. And then when I look at this and say, okay, well, I've got my n initial, it's 4. I got my Z, it's 1. RH is a constant. There's nothing that relates to wavelength here, but then I can remember that my energy of a photon is equal to the absolute value of the change in energy of an atom, so I've got that relationship. And then I have one more thing, my energy of a photon is equal to hc over lambda, so I can, like, relate. I've got wavelength in there, I've got photon in there, I've got my energy of the atom in there. But I still feel pretty stuck because I still don't know what the end final is. Hey, come in, grab a chair. I still don't know what the end final is. And that's where there are some extra hints inside the problem that I didn't write down as explicit at first that actually are really important. Shortest emitted. Right, so let's go ahead, and for me, again, I like drawing pictures. Pictures help me think about things. So I draw the exact same picture that I just erased, where I have my n equals 1, n equals 2, n equals 3, n equals 4. So I know I'm starting here at the n equals 4. Now I'm going to do the shortest wavelength, emitted. The word emitted means that I have to be going down. So my answer is going to be 3, 2, or 1. 2 or 1. I don't know which yet. Oh, I see you were answering. Okay. So now what we have to do, so I know it's going to be 3, 2, or 1. So if we were on an exam, you know, if there was an option that was like 5, 6, or 7, we'd know that wasn't possible because it's emission, not absorption. Right? So that word actually is important. Now the other thing that becomes important is shortest wavelength. Is the shortest wavelength the biggest energy or the smallest energy change?
It's going to be the biggest energy.
It's the biggest energy change, right? And the reason is because our photon energy is inversely related to wavelength. So a bigger energy is a smaller wavelength. A smaller energy is a bigger wavelength. So it turns out from those two underlined words, I actually know n final equals 1. Because that's going to be my biggest energy change, and that's going to give me my smallest wavelength. And at that point, now we're just plugging stuff in and doing solutions. And this one, because the absolute value is sometimes tricky for me, this one I actually do plug values in first, and then after I get rid of the absolute value, I'll do some rearrangement. But we need to do some getting rid of absolute value. So I'm first going to just calculate my energy of the atom, which is going to be -1 is going to be 1 squared, but a negative, which is just going to be negative, oh, I just forgot that number. What's Rydberg's constant? 2.18, thank you. And then my n final is a 1 over 1 minus a 1 over 16. So that's going to be 15/16 positive times a -2.18. That's going to be, I lost my calculator, so I plug that all in. 2.18 times 10 to the -18 times 15 divided by 16. And I'm going to get my energy of the atom is equal to -2.04 times 10 to the -18 joules. Now, it makes sense that my energy is losing, that my atom is losing energy because I'm going from 4 down to 1. So it's kicking off energy, it's losing energy, becoming more negative. So it loses energy. My photon, though, has to be positive energy. So when I relate these two things to each other, I'm going to go ahead and say my energy of the photon is equal to the absolute value of -2.04 times 10 to the -18 joules. Get rid of the absolute value and say my energy of photon is equal to 2.04 times 10 to the -18 joules. The absolute value just gets rid of that negative sign for me. And then I do my rearrange where I'm going to have lambda is equal to hc over energy of the photon. And I plug all of that stuff in to calculate my lambda, and then we'll do some unit analysis. So I do 6.626 times 10 to the -34 times 2.99 times 10 to the 8th divided by 2.04 times 10 to the -18, and I get 9.71 times 10 to the -8. Units of meters, because the speed of light was in meters. Energy of the photon is in joules. That cancels out with Planck's constant. The 1/seconds, and the speed of light cancels out with Planck's constant. I'm just left with meters. Is that part good?
Yeah.
So notice the trick here, the tricky part of this problem was not the algebra. It wasn't just plugging the numbers. It was realizing that shortest emitted told us the end final. Right? Without that realization, that importance of the vocabulary, which is part of why I stress studying the vocabulary. And notice, studying the word shortest wouldn't have gotten you there. Right? It's recognizing how shortest relates to the problem and kind of that deeper contextual meaning of it. But without realizing that shortest emitted gave us end final, problem's impossible. That was really the key part of the problem, was realizing that there's this relationship because we know the behavior of a hydrogen atom and its quantized energy levels. Good?
Yeah.
Okay, let's look at how we convert. I'm going to erase most of this, and we're going to look at how we do some conversions. And I'm going to do this conversion kind of in 3 different ways. And the last way is my favorite way. So we're going to convert this wavelength to a couple different things. So we've got a wavelength equal to 9.71 times 10 to the minus 8 meters. I want to get it to nanometers. Once we're really familiar with our units, knowing what nano means, there's a really quick way to do this. I'm not going to show you that yet. We're going to do a couple of the longer ways first. So the thing that we need to know here is that 1 times 10 to the positive 9 nanometers equals 1 meter. Or I could also write that as 1 nanometer equals 1 times 10 to the minus 9 meters. And this part messes people up because they lose track of whether it's supposed to be the positive 9 or the negative 9 and which way it goes. Nano is small, so it's a lot of nanos to make 1 meter. Or nano is small, so a very small number of meters in 1 nanometer, right? But that's the first thing, is getting those prefixes. Then recognizing which way we need to rearrange this. Since it's already in meters, I'm going to want it in nanometers. So I'm going to use this first one. I think this first one is going to be a little bit easier. So I'm going to have 9.71 times 10 to the minus 8 meters. Actually, I'm going to do this one. No, let's do this first one. Times 1 times 10 to the positive 9 nanometers for 1 meter. The reason I like this one when I'm doing it this way is because I mess up fractions in my calculator. Right? There's too many. If I mess up my parenthesis, I'll get something totally weird. So I like to keep things on top of the fraction as much as possible so I don't mess up in my calculator. And this is going to give me 97.1 nanometers. And so there's kind of always 2 or 3 steps to doing our unit analysis, right? Or our unit conversions. It's what units I have, what units I'm getting to. That's the first step. And it's what is my conversion? And then what's the right way to set that up to make the conversion happen? Right? Because I could have done it the other way. I could have had 1 nanometer is 10 to the minus 9 meters. And that ability to flip the fraction is usually what messes people up. Is this whole idea of like, well, when do you use 10 to the minus 9? When do you use 10 to the positive 9? It's like, well, which way are you setting up your fraction? Both work as long as you set it up correctly. Let me show you my ultra shortcut for how I do my unit conversions after we get a little bit comfortable. 9.71 times 10 to the minus 8 meters. I'm going to move the decimal place over 1, so it becomes 97.1 times 10 to the minus 9 meters. Right? And I'm always looking for my minus 9, my minus 6, my minus 3, my minus 2, those common ones we have. Or my plus 3, that's the other one we use, the kilo. Then I just take this times 10 to the minus 9, and I say 97.1 nanometers. Because I know that 10 to the minus 9 is nano. To do it in 2 steps is to recognize that I'm just doing 1 nanometer divided by 1 times 10 to the minus 9 meters. My 10 to the minus 9 cancels out. So what I do for a lot of my unit analysis, when it's just you changing like those prefixes of the nano, micro, and all of that, is I just make it so my exponent matches the exponent of the unit. And then I just erase the exponent and I put the letter in to represent it. So let me show you another one for how I do that real quick. I'm going to erase this work in green if that's okay.
Yeah.
So one of the things we dealt with last week, 2 weeks ago, was micromolarity. So we had something that was like 40.2 micromolarity, capital M, micromolarity. Right, and so you can do the whole conversion of like, oh, micro is 10 to the minus 6, I write my fraction in, blah, blah, blah. I actually just do this. I do 40.2 times 10 to the minus 6 molarity, because that's what micro means. And so part of the way I'm able to do conversions on the board, or like someone does a calculation, I'm like, oh, it's this in nanometers. The way I do it so quickly is I'm just using that Latin prefix, those prefixes, to figure out what the exponent is. So when someone gives me a length that's like 4.2 times 10 to the minus 7 meters, I'm like 420 nanometers. Because I moved my decimal place over twice, and now it's 420 times 10 to the minus 9 nanometers.
Is micro always negative?
Yeah, right? And so it's that being familiar with those, and there were a few that I said were really good to know. Kilo is 10 to the positive 3. Centi is 10 to the minus 2. Milli is 10 to the minus 3. Micro, 10 to the minus 6. Nano, 10 to the minus 9. I almost skipped it. I almost went 10 to the minus 12. Pico, we don't use pico really, but pico's negative 12, femto's negative 15, atto's negative 21, or 18. I might be off by order of magnitude there. But there's more, right? And we go from kilo to mega, giga, tera, right? Keeps going bigger and keeps going smaller. But these are the 5 that we use most often in this quarter. And this is my trick for doing the conversions really quick. And in your calculator, you can put 40.2 times 10 to the minus 6 into your calculator, no problem. It'll immediately convert it to 4.02 times 10 to the minus 5. It means the same thing. It's fine. So that's like that's some of the quick tricks. One of the things to be careful about is still volumes, right? Because one of the things that messes people up is the fact that the volume, when you're doing a volume element, you're converting once, twice, 3 times. So you have to have that unit conversion cubed because you're doing it 3 times. Did that help? Was that enough?
Yeah.
Okay, cool.
Yeah.
And then we can do more later on, and I'm hoping more come up in more of the problems. But we're moving on to 3.2, which actually gets a lot of conceptual, so we probably won't have a lot more unit analysis problems. Okay, should we go to 3.2? Sure. Okay, let's do it. Okay. Who's got 3.2 number 1 for me?
So it's, what is ZF? And then why is ZF smaller than Z? What happens to the ZF across the periodic table and why?
Did I get your question already?
What?
You okay?
I got my first question, yeah.
Awesome, great. Bum, bum, bum. Concept questions. So what's ZF?
Is it effective nuclear?
Effective nuclear charge. What does that even mean? Right, so this is this is kind of, again, key terms vocabulary. What do we mean? Well, let's think about this kind of in two steps. What do we mean when we say nuclear charge? There's a chair in here too if you want to come in. What does nuclear charge mean? Yeah, it's that obvious. Just say it. You're right.
The nuclear charge rate? Like,
Yeah. The charge of the nucleus. That's it. It's just like, it's like, what does nuclear charge mean? It means like, okay, at the center, I've got like, let's say we've got a +6. We're doing carbon. That's my nuclear charge. I've got my n=1 shell, and then I've got my n=2 shell. Effective nuclear charge, right? So my nuclear charge is +6. This has like 1, 2, 3, 4 electrons. This has like 1, 2 electrons. If I brought another electron in, would it feel the full attraction of that +6? You're shaking your head no. Why not?
Because of the shielding?
Yeah, the shielding. What's another way that we could say it? If we wanted to use like less vocab terms, maybe it's more physicsy, but there's shielding. What do we mean when we say there's shielding? What's this electron going to do to this electron? Pull it towards or push it away?
Push it away.
It's going to push it away. So we've got a repulsive force from these electrons pushing on that electron versus the attractive force of the nucleus to the electron. Right? So we've got this push and this pull going on. And so the effective nuclear charge, right, the nucleus is a +6 no matter what that electron outside thinks or feels, or like attractive force acting on it if we want to be less, anthropomorphizing, because the electron doesn't feel anything, doesn't have emotions, but it has a force acting on it, right? So if we wanted to think about this, like the nucleus and the nuclear charge is 6 no matter what the force acting on that electron outside is. So we say, okay, well, it's the outside electrons that we mostly care about, that we're mostly interested in understanding like the forces acting on them, because that's where we see a lot of our reactivity behaviors in those outside electrons. So we say, okay, well, that outside electron is not going to feel the entire 6 +6 charge pulling on it. It's going to feel some amount of reduced attraction from the shielding, where the shielding is that amount of, it's more than just the electron repulsion, but that's a big part of it, is that electron repulsion, the other electrons pushing it away. And so that's why Z effective is always less than Z, right? Because Z, our nuclear charge, is the maximum possible force it could feel. And then all of the electrons are going to reduce that attractive force by a little bit more and a little bit more. And you're never going to have an attractive force bigger than the full nuclear charge. So, always ends up smaller. Now, what happens as we go across the periodic table? So let's see here. Let me erase this a little bit, kind of get rid of our first kind of conceptual idea, and get back to carbon. Okay, so here's carbon. I'm going to draw a couple different things. Here's carbon. I'm going to have to draw it smaller so I have space. I'm going to draw carbon, nitrogen, and oxygen so we can understand what happens as we go across the periodic table. So here's carbon. I've got my +6 in the middle. I've got my n=1 with 2 electrons. Then I've got my n=2, which has the s and the p electrons in it. Technically, we draw those as different orbitals and different subshells, but I'm just doing it as shells right now. Then I've got nitrogen. Now, when I look at nitrogen, I've got a +7 in the middle. I've got my s, I got my n=1 with 2 electrons. And then I got my n=2. And I'm going to have 1, 2, 3, 4, 5 electrons there. Then I'm going to go to oxygen. That's going to be a +8 in the middle. Got my N equals 1 with 2 electrons. And I got my N equals 2. Sorry, the sizes should be all the same-ish, but I'm running out of space. This is going to have 1, 2, 3, 4, 5, 6 in that N equals 2 shell. And then just for fun, oxygen, fluorine, neon, I'm going to do sodium. And I think this, well, I'll do let's do sodium. Sodium is going to be a +11 in the middle. It's going to have its N equals 1, its N equals 2, and I'm going to draw it a different color to be dramatic. It's going to have N equals 3 with 1 electron there. So the question becomes, and this is an oversimplification, it's Bohr model, but remember Bohr model works pretty well for us, like 70% of the time. Bohr model's good enough. Don't need to go to quantum theory and all of that to just get this idea of what's happening with shielding. Could probably be more accurate, good enough without having to do quantum theory though. So when I look at this and I say, okay, when we were talking about the effect of shielding, we were talking about an extra electron coming in. But I can use it to talk about what kind of interactions is happening with the electrons in this valence shell of the carbon. So I can calculate approximately my Z effective for carbon is going to be the 6 in the middle. This is approximate. There's a lot of approximation happening here. And it's going to be there's only 2 electrons blocking these. So it's going to be like 6 minus 2. It's approximately equal to 4. Right? So these electrons, and that makes sense because 4 electrons are attracted. Technically, these electrons are also pushing against each other, and you've also got the energy of the orbitals. So it should be less than 4, but approximately true. When I look at nitrogen, I say, okay, well, what's my Z effective for nitrogen? Here, have I increased my amount of shielding? Come on in. There's chairs here. You guys can come in. Have a seat. Come in. Or did you want to talk about something else? Yeah. Okay, I'll be out in just a second. Hang on just a minute. So here, have I increased my amount of shielding, my number of core electrons? Right? When I look at these outer electrons, technically they're pushing against each other, but when I look at how much is blocking them from the nucleus, it's still just about a -2. But my nucleus has more charge now. So that's like a charge of 5. Whoops, sorry, 7. I did the math in my head too fast, sorry. The nuclear charge is 7. There's still only 2 core electrons in there. So this ends up being approximately 5. Increased nuclear charge, effective nuclear charge, as we go from carbon to nitrogen. And that happens because we're increasing the nuclear charge without really having a big impact on the shielding. So we're increasing the nuclear charge with having very little impact on the shielding. So our effective nuclear charge is going up, which means we've got stronger attraction to the nucleus, which means carbon is going to be bigger than nitrogen. Nitrogen is going to be smaller. It's got more electrons, but nitrogen is smaller, which is weird because you'd think the thing with more electrons would be bigger. It's got more electrons, but it's smaller because it's got that increased nuclear attraction. Okay, I'm going to skip oxygen. Oxygen does the same thing. You go up to 8, but this ends up being approximately 6. I'm going to go to sodium, and again, I'm going to change colors to be dramatic. Here, when we go to sodium, we've filled our N equals 2 shell, and now we have to go all the way up to N equals 3. Has my amount of core electrons changed? Has my shielding changed? By a little or a lot? It was 2 here. It's 10 here. Our shielding has gone up dramatically. My shielding has jumped up. Because I have to go to that next shell out, my shielding has increased. My nuclear charge is still 11, but my shielding has increased dramatically.
But so you also count the 2 in.
Yeah,
Oh.
everything inside there. So the 2 in the n equals 1,
And
the 8 in the n equals 2, those all count as core electrons that are going to shield. So if I'm looking at just that green electron, the outer shell electrons, the valence electrons, those are all synonyms for each other, of sodium, the effective nuclear charge, again, this is approximate, the effective nuclear charge drops down to 1. So we see an increase in the radius to sodium for 2 reasons. One, we've gone to the n equals 3. We know n equals 3 has a bigger radius. 2, the effective nuclear charge has just had a dramatic drop. So not only are we in n equals 3, which we know is bigger, but the attraction of that electron to the nucleus is weaker than we saw in the previous elements. Because that effective nuclear charge, because that dramatic increase in the shielding, those core electrons pushing away.
So to summarize, an increase of a radius is the what's E? Hold on, what was it? There's a drop as the radius increases.
So we have to be we have to be really careful with our vocabulary because there's like 5 things happening. So make sure you've got it really written out clearly. You know, whenever we say it's dropping as the other thing is increasing, we have to say which thing is increasing, which thing is dropping. We have to be really careful with our language here because there's so many things going on. The simplest relationship is that as effective nuclear charge increases, radius decreases.
Wait, so radius increases, attraction becomes weaker?
If radius is increasing, it's probably because there's weaker attraction. There's 2 reasons that radius could increase. It could be because we've changed which shell we're in. That's just related to the solving those equations that we avoided. Right? So it could just be because we've changed the shell. That causes an increase in radius. Also, if we decrease the nuclear attraction, we usually see an increase in radius. The reason I say it in that order, you said it in a different order. And we have to be careful because an increase in radius could mean 2 different things. So if we see radius increase, it doesn't just mean nuclear charge has decreased. It could mean that, but it could also mean different n value, a couple other things. So it's not either direction. There's like a one direction for that logic. So that's kind of, and this is going to be an important idea, right? This effective nuclear charge, it relates to radius and gives us information about that radius information. It relates to ionization energy, right? If your effective nuclear charge is smaller, it's easier to remove that electron because it's less attracted to the nucleus. So our ionization energy can also be related to this effective nuclear charge. So it becomes a really useful kind of idea. It's a little bit more difficult to relate it to electronegativity, that really important thing we talked about at the end of class on Thursday, because electronegativity is a combination of multiple ideas. But it relates to ionization energy and electron affinity. So it does relate, since the effective relates to ionization energy, Z effective also relates to electronegativity, roughly. A little bit more complicated than that, but it still relates. So this idea becomes pretty important. Is that good for this one? Are we ready to go to 13 and 14? Okay. I'm going to pause. I'm going to let you all talk about 13. Well, let me put 13 on the board, and I'll let you all talk about it while I talk to somebody else real quick. Who's got number 13 handy?
I do.
Great.
So it's named this salt, NH4 in parentheses, and 2S
Where's the 2 go?
in front.
Here?
Yeah.
Subscript. Okay. I'm going to let you all think about that for a minute. This is something we're going to talk about today with learning. Like, this is vocabulary key terms, and we'll talk about this more today, but I'm gonna let you think about that and talk to each other for a minute. So, process of naming is there's a flashcard game on atom.calpoly.edu that you can play on your cell phone to help learn this vocabulary. This would just be ammonium sulfide.
What website?
Atom.calpoly.edu. It was that site that I told you all to bookmark the first day.
Oh yeah, that one.
It only works when you're on campus.
Oh really? Oh, it's kind of
I
weird.
tried to look at the office hours off campus, and it didn't let me. Like the page was blank, and then someone told me that it only works when you're on campus.
It might have like a local security thing. But that's one thing, and then I'm also gonna bring some nomenclature pages to class tonight so we can start learning that. The nomenclature will not be on this midterm, but it will be on the next midterm.
Where is it on the website?
On LabPal, if you scroll down to the very bottom, there's the. Oh, on this one,
Yeah.
it is the polyatomic ions flashcards. Okay, but let's do the quiz 1 problem before you have to run. Can you read the prompt to me real quick?
Yeah. A 100 milliliter graduated cylinder has an inner diameter of 19.6 millimeters. What is the vertical distance between the 1 milliliter marks on the side of the beaker? Give your answers in centimeters.
Whoa. Okay, so this question, it'll be curious, what answer did you get?
198.86.
Do you know how big 198 centimeters is? That's like 200 centimeters. That's like 200 inches. How big is that? That's like a lot of feet. Let's see, 198 centimeters, it's 2.54 centimeters per inch, so divided by 2.54. I didn't do my conversions correctly. It's like 79 divided by 12. That would be 6 feet between the marks on this cylinder. So clearly, like, you know, it's like, oh, something went wrong. Where did it go wrong? So this problem, this was on the mastery questions and on, it was one of the graded problems on the mastery questions, and then it was on the quiz, so this kind of come up a lot of times. I'm going to do it kind of quick because I know you're in a hurry, but there's essentially 2 tricks to it. One is that we know the volume is 1 milliliter, which is equivalent to 1 centimeter cubed. Also, we know that it's a cylinder, so we know the volume is a circle times the height. And we want to find the height. My radius, I'm given the inner diameter, so I can do 19.6 millimeters. I can convert that to 1.96 centimeters. And then I can divide it by 2 to get my radius is equal to, that's going to be like 9 point something, 1.96 divided by 2 is 0.98 centimeters. So I know my radius, then I can do 1 centimeter cubed is equal to 3.141 times 0.98 centimeters squared times h. Notice when I divide all of these numbers over, I get h alone. 2 of my centimeters cancel out, and I just get centimeters. That's the fast way to do it. Usually when I do this problem, I take like 5 minutes to do it and slowly think through it. But I've done this problem a couple times in office hours, and I also know you're in a rush. So we end up with 1 divided by 3.141 times 0.98 squared is equal to h. Let's see what we get. 3.14, let's do this. 0.98 squared times 3.141, that inverse. I get 0.33 centimeters. A little bit more reasonable. So 0.33 centimeters. That's like 1/10 of an inch. It's like a little, which when I'm looking at this thing, I'm like, Oh yeah, that kind of, it looks like 1/10 of an inch-ish. Right, so having some like physical reality that we can think of, something that we can look at, that really helps me kind of get a, like, is my answer reasonable? Now, is it okay if I take a look at the work you did? Did you do something close to this?
Yeah.
Let me take a look and see if I can find an obvious typo someplace. Oh yeah. So you went from 1 centimeter cubed to 600 centimeters cubed. Where'd that 600 come from?
Can you hide it from the?
Yes, the numbers can be different. But
Yeah, that's okay. I just want to see
I
how
guess
those
I
work
saw the
this time.
600 and I
If
can
that's
do
okay.
600.
But it was a different problem.
Yeah, it was a different
Oh,
problem. Yeah.
okay. Here. So yeah, that's that problem. Answer's at the bottom. I'm gonna pause the recording again. Okay, one more thing. So I just handed out, and I'll hand out more of these common nomenclatures. You can also get them on LabPal if you want. It's already there. You can get access to it all quarter. So when we are naming compounds, there's a couple things we have to look for. Always look for our common polyatomic ions. The other thing that's going to be really important, which is what we just ran into, is look for charge balance. So when we look at sodium sulfate, you had it written down as NaSO4. The problem is, sodium, when we look at ionization energy, electron affinity, how it exists in the natural world because of its electronegativity, sodium is typically a +1, sulfate is typically a -2. So if I had a +1 with a -2, I wouldn't be charge balanced. I'd have negative charge left over. The only way to fix that is if I have 2 sodiums. Now I've got 2 +1s balancing out that -2. My overall charge is going to be 0 charge overall. And so that's what I mean when I say charge balanced. The fact that my cation charge and my anion charge adds up to a total charge of 0. And you can see the same thing is happening up here. My NH4 typically has a charge of +1. My S typically has a charge of -2. That's why it needed the subscript of 2 there. Now, in these cases, for these ionic compounds, I don't say 2 sodium sulfate, I don't say disodium sulfate. I let the information, I let the fact that I know the common charges dictate the subscripts. We only specify the number of things attached in situations when there's lots of possibilities. That's going to be covalent compounds. So when you talk about nitrogen monoxide or nitrogen dioxide, that's because those covalent compounds have more than one option. We haven't gotten there yet, though. But that's why we don't do it here, even though in your head you're like, I thought we say how many there were. Different categories of compounds have different naming rules. Not to make it more confusing, but to make it so that the name more accurately communicates more information. Like if you hear someone say nitrogen dioxide, you're like, oh, well, it's got di in it, it's probably a covalent compound. Like the naming process is giving you information about the compound. Okay? Question?
Yeah, so I thought in class you said we could use like graphing calculators for the exam. But
Yes.
then on LabPal it says like non-graphing calculators.
Oh, I haven't updated the LabPal since I changed my pal. I was the last, I think I'm the last person in the department to ditch the non-graphing calculator rule. I don't like graphing calculators. But it's I've been convinced that most of the students don't know how to program their calculators. Some of the newer calculators, some of the really fancy calculators, like you can actually like upload a textbook to it. But a student who does that spends so much time flipping through their calculator that they're not really going to do well on the exam. So I was convinced, and I'm finally like, okay. And then as soon as I started being like graphing calculators could be used, I had like 3 students that had calculators that had Wi-Fi capabilities. that had like could connect to the internet. And I was like, that's not okay. It turns out it wasn't as bad as I thought. They went to like some fancy high school where they had these special calculators where there was essentially an instructor calculator that could send problems to their calculators. And like the teacher could do problems and like they could see how the teacher was doing it in their calculator on theirs. But the calculators could communicate to each other. And I'm like, that's not okay. So the way that I'm like, cell phones can't be used, iPhones can't be used, you know, like anything that can connect to Wi-Fi, can connect to other devices, can't be used during the exams. So that's that.
I was wondering if you're gonna post quiz 2. Like.
Yeah, I meant to do that and then I just kept getting one thing after another. I'm gonna go ahead, I'm gonna stop this recording if that's okay.